Hey everybody, welcome to XNT 304, Modernizing .NET Applications with Purpose-Built Databases. I'm one of your hosts, Chad Tyndall. I'm a Principal NoSQL Specialist Solution Architect, and I focus primarily on the DynamoDB database that we have here at AWS. And my colleague here, Thor, is going to introduce himself and kick off the presentation.
And I'm Thor Giddings. I am the leader for the .NET Developer Advocacy here at AWS. So today we'll talk about what's different with modern applications and their requirements and why AWS databases are purpose-built for them. Developers are building highly distributed and decoupled applications, and AWS enables developers to build these cloud-native applications by using multiple AWS services for scale, performance, and manageability. If you think about it, back in the 1960s and 70s, mainframe was a predominant way to build applications. This lasted until the 1980s, when client-server was introduced and significantly changed the way applications were built. Applications started to become more distributed in nature, and the underlying data model was predominantly structured, and the database was often a monolith. Then the internet arrived in the 1990s, and as a result, three-tier application architecture emerged. Client and application code became more distributed, yet the underlying data model was still predominantly structured, and the database remained a monolith. The thing I like to point out here is, if you think about it, for almost 3 decades, people typically built applications against a single database. And that is an interesting data point because if you've been in the industry for a while, you'll often bump into folks whose mental model is, hey, I've been building apps for a long time, and this is always against one single database. So what has changed? Fast forward to 2021 and microservices architecture are how applications are built in the cloud. And microservices have finally reached the database. This allowed developers to do what they do best. You're breaking down those large applications into smaller services and picking the right tool for the job. They want to try to avoid single, overburdened databases with one storage engine and one compute engine, trying to handle every single access pattern. The expectation for builders, as well as end users of today's applications, is really different from the way it was 20 years ago. The latency requirements are much lower, and they're expected to be able to handle millions of transactions per second and many millions of people trying to use the application simultaneously. These expectations have resulted in data management systems that specialize with specialized storage and compute layers optimized for given use case and workloads. This is so a developer never has to trade off functionality from performance or scale. Plus, what I've seen over the last few years is that more and more companies are hiring technical talent in-house to take advantage of the huge wave of technology innovation that the cloud is providing. These builders are building not in the monolithic ways of the past, but with microservices, where they compose the different elements together using the right tool for the right job. All of this has led to highly distributed, loosely coupled application architectures that we're seeing power the most demanding workloads in the cloud. So if you think about it, a number of factors are contributing to the performance, availability, and scalability and the requirements of those of modern apps. If you think about the users, user growth is commonly a key performance indicator for businesses. And the cloud's global reach enables businesses to touch millions of new customers. If you think about it from a data volume perspective, businesses are capturing more data about their customers to either increase the value of their existing products or sell them new products. This results in terabytes or even maybe petabytes of data scale. If you think about it from locality, businesses are often expanding their presence into new markets to reach new users, which complicates the architecture of their solutions and their products. From a performance perspective, these businesses don't want to dilute the user experience in order to reach new markets or grow their customer base. As our former CEO, Jeff Bezos, often says, customers are always beautifully, wonderfully dissatisfied. So if customers find a better alternative, they'll use it. Request rate. As businesses use the cloud's global reach to develop more interactive user experiences, In more markets, they need their apps and databases to handle unprecedented levels of throughput. If you think about your applications from an access and scale perspective, as you embark on your digital transformation, the measures of scale are compounded by the number of devices that access your applications. And we're talking about billions of smartphones in the world right now. And mobile is the bare minimum expectation in 2021. Businesses are connecting cars and manufacturing plants and devices in our homes and everything else you can imagine to the cloud. Think about your house right now. How many smart devices do you own, right? And that's going to keep growing with time. And we're talking about billions of devices that are connected to the cloud. And if you think about it from an economic aspect, your business can't invest millions of dollars in hardware and licenses up front and hope you'll be successful. That model just doesn't work in 2021. Instead, you have to hedge your success by only paying for what you use without capping how much you can grow. These dynamics combined have changed the way businesses build applications, and these modern applications have wildly different database requirements, which are more advanced and nuanced than simply running everything in a relational database. So seldom can one database fit the needs of multiple distinct use cases. The days of the one-size-fits-all monolithic database are behind us, and developers are now building highly distributed applications using a multitude of purpose-built databases. They're doing what they do best. They break down complex applications into smaller pieces and then picking the best tool to solve each problem. The best tool for the job usually differs by use case. Take the case of Amazon.com. Amazon.com took this approach when it migrated 75 petabytes of internal data stored by nearly 7,500 Oracle databases to multiple AWS database services, including Amazon DynamoDB, Amazon Aurora, Amazon Relational Database Services, or RDS, and Amazon Redshift. The migrations were accomplished with little or no downtime. They covered 100% of our proprietary systems. This includes things like complex purchasing, catalog management, order fulfillment, accounting, and video streaming workloads. We kept careful track of the costs and the performance and realized the following results. From a cost reduction perspective, we reduced our database costs over 60% on top of the heavily discounted rate we already negotiated based on our scale. Customers regularly report a cost savings of up to 90% by switching from Oracle to AWS. From a performance perspective, latency on our customer-facing applications was reduced by 40%. And from an administrative overhead perspective, the switch to managed services reduced database admin overhead by 70%. So with that, I'm going to hand it over to Chad for the next section.
Why do we want to consider purpose-built databases? Well, for decades, the only database choice was a relational database. So no matter what the shape or function of the data in the application, the data was going to be modeled as relational anyway. Instead of the use case driving the requirements of the database, it was the other way around. Now, relational databases aren't always the best fit for your application, either from a performance or availability point of view. And we want to make sure that we provide a database which works well given the requirements of the application. So now that developers are building highly distributed and decoupled applications, AWS enables developers to build these cloud-native applications by using multiple AWS services for scale, performance, and manageability. So let's look at what the purpose-built databases that we offer are. Here at AWS, we've taken a strategy of building different purpose-built databases so that you can choose the right database for your use case. And we have 8 main categories, from relational, key value, document storage, in-memory storage, graph databases, time series databases, ledger databases, and wide column databases. And we're going to dig into some of these and really talk about why we would choose one versus the other. But the key thing here is if you're using these different technologies today, you can continue using your existing drivers and code and just plug into our managed services. And if it's a new technology like QLDB or TimeStream, no worries. We have built NuGet packages on the .NET Standard 2.0 so you can adopt those purpose-built databases with both your .NET Framework and your .NET Core applications. Two of the main ones up front that we want to talk about are Amazon Aurora and DynamoDB. So first, Amazon Aurora is a purpose-built for the cloud MySQL and PostgreSQL compatible relational database that combines the performance and availability of traditional enterprise databases with the simplicity and cost-effectiveness of open source databases. Amazon Aurora is up to 5 times faster than standard MySQL databases and up to 3 times faster than standard PostgreSQL databases. Though it does provide the security and availability and reliability of commercial databases at around 1/10 the cost. It's fully managed by the Amazon Relational Database Service, or RDS, which automates the time-consuming administration tasks like hardware provisioning, database setup, patching, and backups. Amazon Aurora features a distributed fault-tolerant self-healing storage system that auto-scales up to 128 terabytes per cluster. It delivers high performance and availability with up to 15 low-latency read replicas and point-in-time recovery, continuous backup to Amazon S3, and replication across 3 availability zones. So if you're tired of dealing with the cost, licensing, and scalability of commercial database products, think about how you can use Amazon Aurora with your .NET applications to run your mission-critical workloads. Amazon DynamoDB is a key value and document database that delivers single-digit millisecond performance at any scale. It's fully managed, multi-region, multi-active, durable database with built-in security backup and restore, and in-memory caching for internet-scale applications. DynamoDB can handle more than 10 trillion requests per day and can support peaks of more than 20 million requests per second. Many of the world's fastest growing businesses such as Lyft, Airbnb, and Redfin, as well as enterprises like Samsung, Toyota, and Capital One depend on the scale and performance of DynamoDB to support their mission-critical workloads. Hundreds of thousands of AWS customers have chosen DynamoDB as their key value and document database for mobile, web, gaming, ad tech, IoT, and other applications that need low latency data access at any scale. One thing I want to add here is that DynamoDB supports a serverless architecture, so you don't need to deal with any hardware provisioning, software patching, or upgrades. There's no version of DynamoDB that you're running on. You're just always on the latest version. So you never have to take downtime or deal with maintenance windows or anything like that. The DynamoDB new features and security fixes and bug fixes and everything, they just roll out in an automated fashion in a way that is totally seamless and transparent to your application. So you don't even know that it's happening. New features just appear, and once they're ready, you can start using them in your application. Now, for decades, people have gotten used to modeling their application's data using relational databases, where they take each entity and they store each entity or object type in a separate table. And those tables then are joined together using SQL queries when we want to access that data in our application. When we model data for a NoSQL database, things work a little bit differently because we need to pre-build any aggregations, we need to pre-join any items that should be joined together because NoSQL databases don't have the join predicate that the SQL query language has. And so what we want to do is we want to think about how we want to access that data inside of our application so that we can create a data model which supports the access patterns that we have. Okay? When we model data for a relational world, we don't really think about the access patterns up front. Right? We just organize this data into tables using third normal form in a way which is designed to minimize the amount of storage space on disk. But when we want to access it and we do these complex join queries, it chews up a lot of CPU time. And in reality, CPU is far more expensive than storage now, because these relational databases, they were designed back in the 60s when storage was the most expensive part of the computing system. But now that hard drives are cheap and storage is cheap, we don't need to worry about normalized forms anymore. We can denormalize our data and store it in a way which will be very fast to access inside of our applications. So we start off by defining the use case that we're going to have. We want to identify the access patterns in our workload. Not just what the entities are, but how do we want to query these entities, and literally down to the level of defining every single query we want to run. We want to access this entity and we want it joined with this other entity on a one-to-many relationship, or we need to be able to count these numbers of entities very quickly, or we want to run other aggregation functions like sums or averages. So what are all the attributes that we need to query on? What are all the entities that need to be joined together? What aggregations do we want to run? And also the next level beyond that is how often does each of these access patterns run? Because some access patterns need to happen millions of times a second, and other access patterns need to happen once a month for some sort of batch reporting workload or something like that. So we might model differently for workloads which need to happen very frequently than we would model for workloads which need to happen in a batch mode or infrequently. Okay, we might create indexes for one and not the other because indexes cost money, and we might not want to pay the money that those indexes require for workloads which happen very infrequently. Now, DynamoDB is really built for OLTP applications, okay, backing websites or REST APIs or things of that nature where users are interacting with the application, sending data back and forth. As opposed to analytics applications or OLAP workloads, DynamoDB doesn't tend to be built and used for those types of workloads. Okay, we have other purpose-built databases like Redshift and Athena, which are really built for analytics workloads. Another thing we want to talk about is what is really the life cycle of your data? Does this data live forever? Is it only really useful for a certain period of time, maybe a couple of weeks or a month or a few months, and after which case it can be safely deleted? If so, DynamoDB has a functionality which is called the time to live functionality, or TTL. And if you use the TTL functionality in DynamoDB, it's a huge money saver, because if you use the TTL to delete your data automatically, then you are not charged for those deletes by the DynamoDB service. So if you do have data which naturally ages out, then using the TTL functionality can save you a lot of money. All right. Sometimes people don't necessarily want to delete their data entirely, but they might want to move it from a very fast, hot data store like DynamoDB into more cold storage in S3. And so you can use the TTL functionality as well to automatically migrate your data from DynamoDB into something like S3 for cheaper, colder storage. All right. And then we need to identify what the primary keys of our entities are going to be. How are we reading this data? How are we inserting this data? And we want to make sure we choose key attributes which are we want to make sure we choose key attributes which give us a nice distribution across the key space, so that we avoid overloading items and partitions too much. For example, we wouldn't want to choose a key which has a low cardinality, like a Boolean value or some sort of status enum value that only has a few possible values. If our key attribute only has 2 or 3 or 4 or 5 possible values in it, distinct values in it, then we'll only have a few partitions to write data into, and it will severely limit the amount of read and write throughput that we can get from the database. So we want to make sure that we choose keys which have very high cardinality, so that we can drive the kind of high throughput that modern applications require. And just to give you an idea of what we mean when we say consistent low latency in DynamoDB, we ran a performance test where we were driving millions of reads and writes per second, and you can see that in the image on the left. Essentially, we started from 0 and we did a nice slow ramp up and down to millions of reads and writes per second. And while we were doing that, we were measuring what the latency or response times that the database was giving our application. And you can see when the test started, we were sort of hovering in this 4 to 5 millisecond response times here, which is still very, very fast. But as the database got more and more heavily used, our response times got faster, which is a little counterintuitive. But the DynamoDB service on the back end is a fully distributed service, and it has different levels of caching built into it. And so the more that we're sending traffic at the database, the more utilized our caches are going to be. And so the database actually gets faster. Most databases get slower when you throw more traffic at them, but DynamoDB is somewhat unique in this way, and it actually speeds up. And you can see the graph on the right drops down into that 3 millisecond response time. Regardless of how much traffic you're throwing at us, DynamoDB is going to give you that consistent single-digit millisecond response time at the P99 interval. All right. Now, we mentioned that DynamoDB provides a multi-region, multi-active functionality. That feature is called Global Tables, and it allows you to replicate your data from your DynamoDB table to DynamoDB tables in other regions. you don't want to think about it like a single entity, which is one global table spread across different regions. You want to think about it like DynamoDB lives in a region, and we keep multiple copies of your data across 3 AZs in that region. And when you turn on global tables, let's say you have it in 2 regions, US East 1 and US West 1, or something like that, we will have another DynamoDB table in that region, and we establish a replication relationship between those 2 DynamoDB tables in those regions. So as you write to the DynamoDB table, say in US East 1, that data will be automatically replicated within 1 to 2 seconds, generally speaking, to the other regions. And then applications that are running in the other regions, say US West 1, will be able to read that data. It should show up within 1 to 2 seconds. These replication relationships are eventually consistent. And there's no real limit to the number of regions that can participate in a global tables replication relationship. So if you have 4 regions that your application runs in and you want the DynamoDB data to be replicated amongst all of those regions, you can read and write in any of those regions using global tables. The other thing is when you enable global tables, the DynamoDB availability SLA increases from its normal 4 nines to 5 nines. So once you have the global table set up, you now have 5 nines of availability SLA. All right, it's very easy to set up. You can start with a regular regional table, and then later you can add regions to it if your application needs it. So you don't have to start with global tables from the beginning. This is something you can just, with a few clicks of a button or an API call or from the CLI, you can enable global tables for just a regular regional table and turn it on. It might take a little bit for DynamoDB service to backfill the data from your source region to the new regions that are in the global table. But once that backfill is completed, you're good to go, and you can launch your application instances in those other regions as well. Now, just to give you a quick snapshot idea of how things work in the back end, DynamoDB and NoSQL databases in general are actually set up in a way that they distribute their total data set across many, many servers on the back end. Some NoSQL databases will call that sharding. In DynamoDB, we call it partitioning. So we will have multiple partitions for your DynamoDB table on the back end. And what we do is we take a hash value of the partition key that you have specified for your table, and essentially that hash value gives us a hexadecimal number. It essentially tells us which partition or which slot this row or item of your table should be stored into. So we can take this row and maybe we store it on these servers over here, which map to partition B, and each row essentially will have a hash value that tells us which partition or which physical servers these are going to live in. This partitioning mechanism is the reason that DynamoDB can achieve this essentially infinite scalability and essentially infinite throughput. Because as you have more data, we just use more servers on the back end to hold your data. As you need more throughput, we just allocate more partitions behind the scenes. Each partition is physical servers capable of servicing a certain number of IOPS. Right now, it's about 3,000 IOPS per second for your table. So if you needed less than 3,000 IOPS for your table, we might just need one partition. But if you need 10,000 IOPS, or you need 100,000 IOPS, or 1 million or 10 million or whatever it is that your application requires, because Dynamo has no limit, we just partition your data across more and more servers horizontally, and that's how we can service larger and larger throughput requirements and data requirements for your application. Okay, now I'm going to hand it over to Thor for him to do one of his demos.
Thanks, Chad, for that. So let's see how we can modernize a single table that lives in SQL Server. Think about this use case. You have a table that has the large percentage of the most volatile data in SQL Server. But you still have things like maybe other applications or business intelligence tools hooked to that SQL Server table, and you don't want to change those apps, right? We're going to show you how you can use DynamoDB to store the data for a single table and use a service called DynamoDB Streams to push asynchronous updates to the original table using Lambda and .NET Core.
So the premise of this demo is that you have a high transaction table hooked up to your .NET application. You want to move that single table over to Amazon DynamoDB to lower the costs, increase the scalability and performance. but you still need your SQL database to contain the updated data. So with that, I'm going to walk you through how to change the application code to use DynamoDB and how to create an AWS Lambda serverless function to process the updates to SQL Server asynchronously. So let's get started. I'm going to use the AWS Toolkit for Visual Studio to interact with my AWS account. You can see here in Visual Studio that I have it installed and I have an IAM profile configured so that I can access my AWS resources without having to leave my Visual Studio IDE. In fact, I'm going to do this entire demo without ever having to log into my AWS account. So the first thing I need to do is I need to add some NuGet packages to my solution. I'm going to add the AWS SDK.core and the AWS SDK.DynamoDB v2. Okay, get those installed. Okay, so those are installed. Let's take a look at the cart model. You can see that I've added a using statement at the top of this class for using the Amazon.DynamoDB v2.data model. And for each property on the object, I've added a DynamoDB annotation to help with the table mapping. I did the same thing for album since album is a property on the cart class. Next, let's look at the shopping cart class. This is the class that previously had all the calls to store the data in SQL Server, and I'll now show you how to move that over to DynamoDB in two different ways. The DynamoDB v2 NuGet package supports two levels of APIs, and you use them based on the task you want to carry out. I'm going to show you the high-level API first. So let's take a look at the remove from cart method. In this method, I'm going to see if I am first removing a set number of albums or if I'm removing the last copy of an album in the cart. If I'm removing a quantity of albums, then I'll just take the first path, and this is pretty easy. I create a cart object, set the cart ID and the album ID along with the count and album object, and call save async to do the update. If I want to simply remove the last copy of the album from a cart, I can simply call delete with the cart ID and the album ID. So that's pretty straightforward. But what if I had something more complicated? What if I didn't know what was in the cart? You can use the DynamoDB low-level APIs to do things at a more granular level. In this case, I'm going to do an atomic update. This will allow me to place an item in the cart without having to worry about how many of the same items are in the cart. So if there are 0, it will add a row to the table. If there are more than 0, it will increment the quantity in an atomic fashion. So the first thing I'm going to do is I'm going to build out the album document that I'm going to pass in. Then I'm going to create the update item request that has 5 main attributes. First is the table name of the table I want to update. Then the keys for the sort key and the range key that I want to update. The update expression, so I'm going to add the quantity that is added to the cart and then set the album. Then I set the attribute names and the attribute values, and then I simply call the update item async, and that's going to do an atomic update for me. Okay, so let's go ahead and create the cart table. And again, I'm doing this with the AWS toolkit for Visual Studio. I'm going to call it cart ID. I am going to use a range key of album ID. Okay, and I'm going to create it. Okay, if I take a look at SQL Server, there's nothing in carts right now. So I go ahead, I run my project. And I'm going to grab an album, I add it to the cart. Now, if I want to see if this is working, I can actually go back in here, and I don't need a custom client or custom driver for DynamoDB. I can actually just double click this cart table and see what's in it. So I can go ahead, and if I see this, I can go, let me add another copy of this record. So now I have 2. And if I go over here and I rescan the table, I have 2. So it's really easy to troubleshoot DynamoDB in that way. So I'm going to go ahead, but our SQL Server, we still don't have anything, right? Because we haven't hooked that part up yet. So I'm going to go ahead, remove some stuff from the cart. If I go in here, everything will be gone. Okay, so I close this. Okay, so let's take a look at the Lambda portion, the part that's going to save that asynchronous updates to SQL Server for me. So the first thing I want to do is I want to use DynamoDB streams to stream images of the items in the table over to Lambda. Now to do that, I'm going to go over to the AWS Explorer. I'm going to right click on the table and I'm going to hit Stream Properties. Now you can do keys, you can do new images, you can do old images, you can do both new and old images, but I only care about the new image. So I'm going to select New Image. Okay. And if I look at my Lambda function, it's really straightforward. What it's going to do is it's going to take these DynamoDB records and it's going to process out the card ID, the album ID, and the count. And I'm going to get from Dynamo whether it's a remove, an insert, or a modify. And then I'm going to just simply go ahead and execute an ADO command against SQL Server, right? So it's a very straightforward function. Now I need to get that into my AWS account. So I'm going to go to the project, I'm going to right click, I'm going to hit Publish to AWS Lambda. I'm going to take a lot of defaults here. I'm going to make sure it's in the same region as where my table is. So I'm going to hit Next. I have a IAM role for Lambda already created, so that gives me access to the resources that I need. But one of the key things that I want to do is, since my SQL Server is in a private subnet, I'm going to give it access to the subnets where the SQL Server is, along with a security group where it can talk to SQL Server properly. So that will give my AWS Lambda function access to my SQL Server. Okay, so this is a screen that it shows you once you have deployed your AWS Lambda function, and you can go ahead and configure an event source right from the screen. So I've added in the DynamoDB cart event source. You can do it just this easily. You just select DynamoDB, you select which table you want to hit, the batch size, and you hit OK. So now that everything's wired up, let's see it work in action. So I'm going to fire up my application. I take a look at my SQL Server. I still don't have anything in carts. I'm going to go in, I'm going to add this item a couple times to the cart. If I take a look at the cart table in DynamoDB, I can see it's there. And if I look at SQL Server, it's also there. Now, if I went in, even if I deleted it, let's say I delete it here, right? So I hit delete, I hit commit changes, I just deleted it from Dynamo. Since the stream is working at the Dynamo level, it'll actually update my SQL Server properly. So it doesn't matter where it's coming from. So that's it for the demo. You can see it's just that easy to modernize a single table without affecting other systems or making wholesale changes to your code. Let's get back to the presentation.
Well, we want to cover a few more of the different NoSQL purpose-built databases that we have in our portfolio here at AWS. The first one up is Amazon DocumentDB, which is a fast, scalable, highly available, and fully managed document database service that supports MongoDB workloads. DocumentDB implements the Apache 2.0 open source MongoDB 3.6 and 4.0 APIs by emulating the responses that a MongoDB client expects from a MongoDB server, which means you don't need a special SDK to talk to it. Essentially, what you're going to do is use your existing MongoDB drivers or SDKs in your .NET applications when you interact with DocumentDB. It looks and sounds and speaks just like a regular MongoDB instance. It's just backed by DocumentDB's decoupled storage and compute infrastructure, which allows you to scale your storage and compute separately. So you can have just one instance in your DocumentDB cluster if you need very low throughput or just need one availability zone, or you can actually add up to 15 low latency read replications in 3 different availability zones if you need to be able to service millions of requests per second in your application. All right. But you don't have to do that in order to add more data. So you can add data independently of how much compute resources that you've allocated for your DocumentDB cluster, which is really nice. Right. It does replicate 6 copies of your data across 3 availability zones inside the region that you've chosen. And you can use the database migration service to easily migrate your on-premises or EC2 hosted MongoDB databases to Amazon DocumentDB with virtually no downtime. Next up is Amazon Neptune, which is our fast, reliable, fully managed graph database. It makes it easy to build and run applications that work with highly connected data sets. The core of Amazon Neptune is a purpose-built high-performance graph database engine optimized for storing billions of relationships and querying the graph with millisecond latency. So you can think about this as use cases like a social network where you want to analyze, friends of friends. Maybe you want to analyze product orders and build recommendation engines for other people, or recommendation engines on, restaurants that you might like, or people who like this also like this. It also uses things like, it's also used in use cases like fraud detection, drug discovery, network security. You can use a package like Gremlin.net in your .NET application to query your Amazon Neptune database through the native Apache Tinkerpop interface. So it's very easy to get up and running with Neptune once you have the data loaded into it. Amazon TimeStream is a fast, scalable, fully managed time series database service for IoT and operational applications that makes it easy to store and analyze trillions of events per day at 1/10 the cost of relational databases. So now that we've had this massive rise in IoT devices, mobile devices, smart industrial machines, the time series data that we need to keep track of has really exploded exponentially, and is honestly one of the fastest growing data types out there in terms of the data that we have to manage. Time series data has really specific characteristics. It typically arrives in time order form. Data tends to be append only, right? It's like sensor readings or things like that coming in, so we don't tend to need to go back and update data from the past. And our queries are generally over a time interval, so we might want to run aggregations on a particular metric, over the last 5 minutes or over the last hour or the last day, what have you. And so we need a purpose-built database that understands these specific query access patterns. And TimeStream does that. TimeStream is serverless, so there's no servers to manage. And it handles all the time-consuming tasks like server provisioning, server patching, setup, configuration, data retention and tiering. Maybe you have, more recent data is queried more frequently, and you want that to be on hot storage. And as data gets older and older, we tend to look at it less often. And so we might want to move that data to cheaper tiers of storage automatically just to save money. And so all of this automated data retention tiering policies that you want to set up, it frees you to focus on just building your applications. So you can use our .NET Standard 2.0 based NuGet packages to read and write from Amazon TimeStream with your new or existing .NET Framework or .NET Core applications. All right, next up is the Amazon Quantum Ledger Database, or sometimes you'll hear us just call it QLDB. QLDB provides a complete verifiable history of all application data changes, and it gives you a few characteristics which really don't appear in any of the other databases in our portfolio. One is that QLDB gives you true immutability. So if you were using something like DynamoDB or DocumentDB or any of the other databases, you could create IAM permissions, which only certain users could only insert data in, and they would not be allowed to update or delete data. But there would always be some sort of administrator user which could go into those databases and update or delete data. With QLDB, it services insert-only workloads, so the actual database gives you true immutability. It maintains a sequence record of all changes to your data written to an append-only journal. So you can really query and analyze the full history of your data and be certain that none of it changed once it was inserted. All data in QLDB is cryptographically verifiable. So the service uses a cryptographic hash function, in this case SHA-256, to generate a secure output file of your data's change history, which is known as a digest. And the digest acts as proof of your data's change history, allowing you to look back and validate the integrity of your data changes. QLDB is a serverless database like many of our other databases, and it scales with the application. Unlike traditional blockchain frameworks, which require a network of nodes to achieve consensus with each other, QLDB performs at a much lower latency and higher throughput, not requiring companies to trade performance for verifiability. You can start using QLDB today with your .NET applications by adding in the amazon.qldb.driver NuGet package. All right, last up but certainly not least on our list here is Amazon Keyspaces for Apache Cassandra, which is a scalable, highly available, and managed Apache Cassandra compatible database service. So just like we had DocumentDB, which is a MongoDB compatible database, and we had Aurora, which is MySQL and PostgreSQL compatible databases, Keyspaces is our Cassandra compatible database. And it's great because just like DynamoDB is serverless and gives you single-digit millisecond performance at any scale, Keyspaces does the exact same thing. It just provides you with the with the Apache compatible Cassandra standard interfaces. So if you're already using Cassandra today in your application and you want to migrate to something which is cloud native and hosted in AWS and gives you the ability to not have to manage servers and deal with the complicated types of rolling upgrades that very large Cassandra clusters struggle with sometimes, then migrating to Apache Cassandra could be a good fit for you. You can use your existing .NET Cassandra drivers and just plug right into Amazon Keyspaces. And for data migration, you can use any of the existing Cassandra data migration tools to move your on-premises or EC2 hosted Cassandra data over to Amazon Keyspaces. All right, I'm going to turn it back over to my partner here, Thor, to close us out.
Okay, so that's a really interesting way to use DynamoDB to solve a business problem. Let's talk about our next database technology. Amazon ElastiCache offers fully managed Redis and Memcached. It allows you to seamlessly deploy, run, and scale popular open source compatible in-memory data stores, build database-intensive apps, or improve the performance of your existing apps by retrieving data from a high throughput and low latency in-memory data store. Built on open source Redis and compatible with Redis APIs, ElastiCache for Redis works with your Redis clients and uses the open Redis data format to store your data. So if you're currently using Redis or Memcached, and you can make your life a little bit easier. Just plug right into Amazon ElastiCache and not have to change your existing .NET code. Amazon MemoryDB for Redis is a Redis-compatible, durable, and that's the key here. This is a durable storage in-memory database that delivers ultra-fast performance. It offers fully managed Redis with durability. MemoryDB is purpose-built to serve modern microservices applications like data-intensive real-time apps, mobile and web apps, media and entertainment, gaming, e-commerce, and retail. MemoryDB is fully compatible with open source Redis. It uses, you can use flexible Redis data structures and APIs like strings and sets and lists. MemoryDB can handle more than 13 trillion, with a T, requests per day, supporting peak throughput of 160 million requests per second. It scales easily from just a few gigabytes to over 100 terabytes per cluster, meaning you can achieve both ultra-fast performance and massive scale. By storing your entire database in memory using a multi-AZ transaction log, MemoryDB enables fast database recovery and restart without the risk of data loss. Because MemoryDB stores your data durably, you can actually use this as a primary database. And again, it's all based on Redis Open Standards, so you can just use your standard .NET Redis driver and plug right in and start using it today. Think about how your search works in your application. For many custom-built applications, you might be wiring up a bunch of complex SQL Server queries to try to determine how to best get the data your users are looking for. But what if there was a better way? What if there was an easier way? Amazon OpenSearch is a distributed open source analytics suite used for a broad set of use cases like real-time application monitoring, log analytics, and website search. Like Elasticsearch and Apache Solr, OpenSearch is powered by the Apache Lucene search library. So you don't need any special AWS drivers for your .NET applications. Just use your standard .NET drivers, connect in, and start using it. The Amazon OpenSearch service has a powerful engine that makes these different use cases possible. For full-text search, it allows capabilities like natural language queries and relevant results. For log and analytics, customers can stream data in high volumes in real time and analyze the data using a variety of filters and visualization options. So here's OpenSearch at a super high level. The data gets sent in a JSON format. Then it's indexed. And finally becomes available for the end user to search and analyze against. But enough talking about it. Let's see it in action. So now we're working on modernize this MVC Music Store application. We're going to swap out the search capability and plug in OpenSearch in this demo.
So for this last demo, we're going to integrate Amazon OpenSearch with our application. Imagine that you had this common business issue. Right now, people can go to your music store and search for genres or artists or albums, and it's pretty basic. But what if you wanted to include the ability to increase the search capability to search for albums? And you can find them by, let's say, artists or genres. So if you wanted to type rock, it would return all the rock albums. This would add a new level of complexity to your SQL code. But take this one step further. What if you wanted to search on track names or even lyrics of a song? You can imagine that SQL is going to get pretty unwieldy. So this is a great use case for OpenSearch. What I did is I ingested all the album data with both the genres and the artists as properties of the album document. And for this example, I also added all the lyrics to the Pearl Jam album 10, one of my personal favorites, to OpenSearch. So let's see it in action. The first thing I'm going to show you is the NuGet packages that I added. So I added both Nest and Elasticsearch.net for the project, so I can access and use the OpenSearch cluster results. Next, we'll look at this helper class. So the search function is going to do a simple wildcard search across all indices. When you populate a cluster, each document will become an index that you can search across. Additionally, we have built an index to model map to pull back the results in a way that the application will understand natively. Finally, we're going to group by the model type and return the results appropriately. So we'll group all the artists together and the genres together and the albums together. So let's go and see how this actually works in action. So I'm going to run the application and I'm going to search for rock. Now it's going to return both the rock genre and then a bunch of rock albums. Okay, how about Maiden? It returns the artist Iron Maiden and a bunch of albums that have the search term Maiden in them. Okay, so let's try a track name from that 10 album. Let's try Oceans. It returns 10. Let's try a track name for something that it's not going to understand, like Nothing Man. Okay, didn't find it. So let's try some lyrics. Let's try Concrete. And there you can see the album again. And it's really just that simple. You can go ahead and ingest all of your data into an OpenSearch cluster, augment that data, and then use it with your existing applications and existing models to get better search back to your customers. And with that, back to the presentation.
So to wrap it up, when you think about this collection of purpose-built databases, you won't find this collection anywhere else. And when you have a company that says, oh, no, wait, you don't need that many databases. I have a relational database. It can take care of all your needs. You should nod and say, And then some companies might tell you, no, I have a non-relational database, and it does key value really well, and it does document really well, and it does, graph really well, and it does, time series really well. You should listen, you should be polite, and you should be very skeptical. Swiss Army knives are very rarely the best solution for anything other than the most simple task. If you want the right tool for the job that gives you differentiated performance, productivity, and customer experience, you want the right purpose-built database for that job. And we have a very strong belief inside of AWS that there is no one tool to rule the world, that you should have the right tool for the right job to make you spend less money, be more productive, and change your customer experience. Please join me in exploring these purpose-built databases with your .NET applications today. I want to thank everyone for listening to this session. I hope you have an awesome day.